So last time we had some technical difficulties when I was trying to record this screencast in class. So I'm back in my office now and I'm going to record it again. The content might be a little bit different from exactly what we went over in class, but it should be pretty close. And so what we're going to talk about today is exactly what we mean when we say turbulent. What is it that's going on when we say the flow is turbulent? And so this will be the last material that we cover on pipe flow. After this, we'll start to look at flow over what are called submerged bodies, which will be things like flat planes and airplanes and spheres and cylinders and that kind of stuff. But for now, we're going to focus on turbulence, and here I've drawn a flow profile that we've probably seen before. It's probably a quadratic flow, most of them tend to be. And I've sketched in a little fluid element there of width delta x and height delta y. And so what's happening with turbulence is if we zoom in on a small portion, and for now I'm just going to talk about this face, and remember this face is the plus y face, because if I draw the normal vector on that, it's going in the plus y direction. So that's how I'm going to refer to that face of this fluid element, is the plus y face. If I zoom in on that, so here's my circle of zooming in, I would still see a boundary here, but what turbulence is doing is taking small chunks of fluid, and actually they can be rather large chunks of fluid, and it's moving them across our boundary. How is it moving them? It's a completely random process. That chunk might get kicked from another chunk moving along, and therefore it gets ejected out of our control volume. You can also have chunks of material getting kicked into our control volume. That's perfectly okay too. But this is what we mean by turbulence. So in laminar flow, there's no way for that fluid to move off of the streamline that it's currently on. When we have turbulence, there is a way for it to move off of that streamline, and it's by these random kicks of energy that occurs at very high Reynolds number, or fairly high Reynolds number, and that will transport a blob of fluid across our boundary. And so the result of this is that all of our values will fluctuate. So which values fluctuate? Almost anything that you can measure, or even things that you can't measure, will be fluctuating in time. There'll be some noise overlaying each of these values. So I am going to talk mostly about velocity, such as Vx or Vy, but other things that are also fluctuating include the pressure. You might measure the stagnation pressure, that would also be fluctuating. The shear stresses on any of the surfaces would also be fluctuating. They're all fluctuating, but we're just going to talk about velocity right now because that's the one that we really need. So if we were to look at, as a function of time, the velocity in the x direction, what we would see if we actually went out and measured this would be that that value has sort of a random motion like this. It's generally non-zero, but it's fluctuating around with random steps. And so I could define a time average value that goes right down the center. If I just add them all up and divide by the number of measurements, I would get what's known as the time average value, which we call V sub x with a bar over it. And so anytime we want something with a bar, we define this V sub x bar, or really anything with a bar, is defined as time averaging something over a certain time period t, which we accomplish by integrating that signal. So V sub x is our complete velocity profile, which is a function of time, and we integrate that with respect to time over some period capital T. And that works for pressure or velocity in any of the other components or anything we want to measure with time. It always looks like an integral that looks like that. Overlaid on top of that average signal, which is flat when we're at steady state, are these little bumps. And so the bumps, these bumps, are the fluctuating values, the time-dependent ones, which are called Vx prime in this notation. So if I want to know what V sub x is, the total velocity profile, what is the x component of the velocity really doing, it's made up of two components. It's made up of the time average one, which we call Vx bar, and it's also made up of a fluctuating value that we call Vx prime. That's in the x direction. In the system that we showed here, notice that the velocity profile is only going in the x direction. So if I wanted to look at the y component of the velocity as a function of time, so here's time, here's v sub y this time. Now I have to include a little bit of a negative line because here the average velocity in the y direction is still 0, but there's a fluctuating component. And so this component is vy prime. There is an average vy for the way that we drew this before. It just so happens that vy bar will be equal to 0. Because on the whole, for fully developed flow, there is no bulk motion in the y direction. But there is a component of the random noise signal, the fluctuating signal, v sub y prime, that does have to be taken into account. And so when I say, what does that mean? How do we take something like that into account? What we're going to look at is the effect of these fluctuations on the momentum balance. And specifically, we're just going to start with the x momentum, and we're even going to limit ourselves a little bit further to just that plus y face that I was talking about before. Because we're just trying to get a qualitative understanding of what is it that fluctuation does to change our momentum. So if we remember from our discussion of laminar flow, if I wanted to sum up the forces in the x direction on the plus y face, remember we're just dealing with that plus y face for now, that would be, at steady state, I have no time-dependent term, so it's just going to look like a flux integral. And that flux integral is going to look like v sub x in the velocity in the x direction times rho times v dot n, integrated over the area. But if we look at v dot n, remember I had a flat surface like this, and my normal vector was going out. In the laminar case, all of the flow was going in this direction, parallel to our surface, and normal to our normal vector, actually. So v dot n will end up being simply v, in this case, v sub y, but in the laminar case, that's 0. So therefore, there was no transfer of momentum across our plus y face in laminar flow. However, now that we move to turbulent flow, we see that the situation changes a little bit. So if I again sum up all of my forces in the x direction, just on the plus y face, remember we would have to do this for all 6 faces, but I'm only going to do it for one here, then I would get the following. I would get another flux integral, except instead of where I used to have just v sub x, I now have 2 terms. So v sub x will become vx bar, which is our average, time average term, plus v sub x prime, which is our fluctuating term. All of that multiplied by rho, and now we look at our v sub y term, and again I get 2 terms. This is actually v dot n, which is v sub y. So I get the time average component of v sub y, plus the fluctuating component, v sub y prime, integrated over the area. Now remember, in the bulk flow that I showed back here, v sub y bar will still be 0. The time average velocity in the y direction is 0. But v sub y prime is not 0. That's a fluctuating non-zero value. So I can cross out v sub y, but I'm still stuck with these other terms. I've got a vx bar, vx prime, and a vy prime. And so there was a very important assumption that we make, which is to time average this entire quantity. So if I draw a time averaging bar over this, I will get a time averaging bar over this term and a time averaging bar over this term. There's a very important approximation. So normally, if I were to take Vx bar and then average that, I would get simply Vx bar again. It doesn't matter if I average an average, I still get an average. If, however, I time average the fluctuating quantity, this would be 0, because the quantities are fluctuating completely randomly. It spends as much time above the average as it does below the average, and that's true for any one of these these fluctuating values. So that's also equal to Vy prime, average. There was a very important assumption by Prandtl, which gives us our way forward. Prandtl, and this was quite a while ago, this was in 1925, and I put the dates in here. We're going to present all of this really, really quickly, and it might give you the impression that somebody just sat down one afternoon and wrote it all down, but this actually took decades of work to figure out that these are the appropriate approximations. So I'm going to mention the time a couple of times here, or the dates. He guessed the following. He guessed that Vx prime is actually related to Vy prime. So the fluctuations in the x directions are related to the fluctuations in the velocity in the y direction. And so as a result, because these two things are correlated, this has a very important implication, which is that if I time average the product of these two fluctuations, not each one individually, but time average their product, this is not equal to 0. And so what that means is I'm going to have an extra term due to the product between this Vx prime and this Vy prime. I'm going to have a non-zero transfer of momentum across that boundary, because Prandtl assumed that when I multiply those two quantities together, they don't perfectly cancel out after I time average them because they're correlated. Remember, the bulk flow is generally going from left to right here, so you can imagine if I kick up in the y direction in this way, I tend to go a little bit to the right as well because the bulk flow is moving me to the right. So that actually creates a correspondence between Vx prime and Vy prime, which is what Prandtl assumed. So as a result, we get the following. We find that the shear stress, tau sub yx, is equal to the same one that we saw before, which is mu dv bar sub x dy. That's our laminar contribution, but Prandtl found that we have this new contribution, which is minus rho Vx prime Vy prime, but time averaged. This, for simplicity, can be represented as the laminar viscosity plus a new term that we call eta, which is the turbulent viscosity, times that same velocity gradient, dvx dy. This term has a special name. This is what's known as the Reynolds stress. So this is the shear stress due specifically to turbulence, and we call that the Reynolds stress. We don't actually use this term very much. We tend to use the eta term over here, but the question is, we do need some sort of an expression for Vx prime, Vy prime. We have to be able to work with that somehow, and as you can probably tell at this point, we've already made a lot of guesses. Prandtl actually went along to guess something else to give us a handle to work with that term. So Prandtl guessed the following model. He said, I think that turbulence works this way, which is usually how science gets started. We guess that it works one way. He carefully evaluated it and went out into the lab and measured it. So what he said was, if I have a blob of fluid here, and that blob of fluid gets kicked, so it moves up a little bit. So let's say it moves up a certain direction here. And we're going to say that it moved a given direction to about here, from about here, and we're going to call that distance L. We don't know what that distance L is yet, but at any rate, when you move from y to y plus L, we can evaluate the velocity difference, which will be Vx bar evaluated at y plus L minus Vx bar evaluated at y, that change in velocity, he said, well, that is exactly equal to the size of the kick we got, which is Vx prime. His assumption was that this is equal to that mixing length, L, times dv bar sub x dy. So he introduced this mixing length parameter, which we call L. This is mixing length. And he went one step further, which is nice because we get to use his results. So he went one step further and said, if I have Vx prime and Vy prime, and I time average these, this is going to be proportional to simply one of these terms for Vx prime and another identical term, this was the assumption, for Vy prime. Remember, these two values he assumed were correlated, so he picks the same functional form, which is this mixing length times a velocity gradient, and he says, well, if I multiply those two together and time average them, I should get something that looks like just that term squared. So he ends up saying, well, I think it should look like L squared times dvx bar over dy squared. I just get one term from each one. That was one of his assumptions. He went on to later say a better approximation for L is that it's equal to k times y, where k is an experimentally determined parameter. So if I plug all of that back into my original equation that I showed up at the top, what I find, is the following, that tau yx for turbulent flow is equal to rho times k squared y squared dv bar sub x dy squared. And when I am near the wall, this is an important approximation as well, we call this tau sub naught, which is a constant if you're at the wall. We'll see how that affects things in a minute. But at any rate, this is the expression that we're going to work with. And this is completely due to the mixing length hypothesis of Prandtl. As a result, this, because, let's see here, this term is constant, tau naught is constant, rho and k are both constants. What we have here is a separable first-order differential equation where we can solve for v bar x as a function of y. So I'm going to rearrange that term a little bit, and what we find, this is nothing but algebra here, I've rearranged it, and isolated dv bar x, or dvx bar, dy, will be equal to the square root of tau naught over rho divided by ky. If I solve that equation, I will get Vx bar is equal to the square root of tau naught over rho divided by k times the natural log of y plus an unknown constant that I'll call C1. This is a very important equation. It gives us the functional form for how we expect a velocity profile to vary in turbulent flow. This form is called the law of the wall. And the important part here is that natural log dependency on y, which is here. Another term to note is this square root term, which I'm just going to highlight in blue. This square root of tau naught over rho, this is sometimes called the friction velocity. Just note that if you work out the units on that, it does have units of velocity. That's why that term keeps coming up over and over and over again. Experimentally, some people went out into the lab remember this is turbulence, so we're really limited with the theory we can do, so there's a lot of experiment that gets factored into this. And so experimentally, in 1943, so I bring up that date again just to let you know, it took about 20 years from the time Prandtl assumed the mixing length model to the point where we could actually measure something useful about it. He found that K was approximately 0.4 near the wall. So hooray, we measured one of those constants. We were still stuck, however, with this other unknown constant, C1. And so that required quite a bit more work, a lot more experiments to finally find forms for C1, and we got a lot of different forms for them. And so this is all going to be presented in dimensionless form. So some people made the following definitions. We defined a dimensionless coordinate, which is y plus, and that is simply equal to y times that frictional velocity term, tau naught over rho, divided by a new quantity nu. So there are a couple of things here. First of all, y here is defined, if you're in a cylinder, y is defined as r, big R minus little r, where big R is the radius of the cylinder. And nu is a different kind of viscosity. It's called the kinematic viscosity, and that's just equal to mu, the same viscosity that you're used to, divided by rho. Sorry, that's called the dynamic viscosity. Nu is the dynamic viscosity. So that's how we define a dimensionless location. We also define a dimensionless velocity, and this will be equal to Vx bar divided by that frictional velocity, square root tau naught over rho. So we've seen this stuff before. If you remember on our last homework with Navier-Stokes for laminar flow, you've seen dimensionless variables before. For laminar flow, I'm going to put this in brackets just so you don't think it was something new. Laminar flow, we would have defined y plus as something more like r over r. Remember, that term showed up a lot when you were non-dimensionalizing your equations, and very frequently we would have had a dimensionless velocity that would have looked something like v sub maybe x over v max. Right? They looked different, and we didn't call them plus, but the important thing to remember is these are just non-dimensional variables. Right? There's no new information here. We just picked a nice scaling system and non-dimensionalized our variables in the same way that we have before, and we have a fancy plus as denoting a dimensionless variable. So once people defined those, they defined, well, they didn't define this, they went out and experimentally measured the following velocity profiles, specifically for turbulent flow. So remember, for laminar flow, oh sorry, this is turbulent flow in a pipe, so turbulent pipe flow. Remember, in laminar pipe flow, we could solve the Navier-Stokes equations and get a single velocity for the entire pipe. So I'm just going to sketch that over here. You're going to end up plotting these profiles as part of your homework. But if I were to plot these profiles for laminar, I'll continue to use blue for laminar, you would have seen that you would get something parabolic. That's not a very good parabola. That's a better parabola. So that would be the laminar profile. What they found was for the turbulent profile, the situation was a little bit more complex. So the turbulent profile, I will give in yellow here, has three separate regimes. So the first regime was what was called the laminar. Sorry, I paused recording there. There was a siren going by. Oh, there it is again. You might hear it. Anyway, the first profile section is called the laminar sublayer. And so in this regime, what people found was that V plus simply looks like Y plus. That's all it was. V plus was Y plus, and this occurs in the regime for when Y plus, let me draw my Y's consistently here so you don't get confused on that. If Y plus is between 0 and 5, in other words, if you're very close to the wall, then V plus looks like Y plus. This is a velocity profile, right? This is equivalent to what we saw before, this is something like saying V over V max is equal to, say, R over R. That's what it would look like in the laminar flow. Here it's a little bit more complex because our variables have changed a little bit, but the important thing to remember is when we say V plus is equal to Y plus, that is just a way of us defining a velocity profile. And we're going to see an example of how to use that here in a moment, but we got to get to the other regimes. So the intermediate regime is called the buffer layer. And in the buffer layer, the relationship between your position and your velocity is a little more complex. Here, V plus has been experimentally determined to be equal to minus 3.05 plus 5 times the natural log of Y plus. So remember, importantly, we see that natural log dependence on Y plus that we got from the law of the wall. The other two coefficients were experimentally determined variables. This regime is valid for when Y plus is between 5 and 30. And then we have our last layer, 3, the very last one, which is called the turbulent core. And so in the turbulent core, we have another velocity profile. Here, V plus is equal to 5.5 plus 2.5 times the natural log of Y plus. And this is valid whenever Y plus is greater than 30. So again, these profiles all have, well, 2 of them anyway, have this natural log dependency that we estimated or we thought was reasonable by our derivation from the log of the wall, but then we ended up having to go out and experimentally determine all of these coefficients. And so you'll always be given these profiles. In fact, you can find them on your homework in that notes section that we have on the top page. And one of the things you're going to have to do is plot this profile, and what you'll find is if you compare it to the laminar profile, it's very, very slow changing near the wall, and then it's practically flat across the channel. And so this is where we get that term plug flow from. This yellow one over here would be the turbulent profile. And that's quite a bit different from the laminar, and it has pretty big effects on the shear stress, for example. But you'll notice a particular problem. If you wanted to plot, say, V plus, let's say you wanted to plot this V plus relationship. In order to know that, you need to know Y plus. And if I go back up here into Y plus, I need this tau naught term in the Y plus, and I also need a tau naught in the V plus. Well, I don't have a tau naught. We haven't gone over how to figure that out. Now we're going to see what happens if I need tau naught. That's the last part of the puzzle that I need in order to be able to evaluate these Y plus terms. Because notice the other terms, this nu is a function of the fluid properties, as is rho, and as is this rho. So if I knew tau naught, I could actually plot this velocity profile, but at the moment, I don't know what tau naught is. Here's how we figure out tau naught. Tau naught, remember, is the shear stress at the wall. So tau naught, we said, was defined as tau yx, or actually, since we're typically working in pipes, this is more like tau rz. This is evaluated when r is equal to big R, which is at the wall. And in order to figure out what that is, we're going to take a chunk of fluid inside of our pipe, and generally that fluid is moving to the right. There is some pressure acting on it. Remember, there's a pressure upstream that we'll call P1. There's a pressure downstream, P2. It's always compressive, so it's acting in on our surface. If I draw my coordinate system in here, this is my central axis. So Z is going this way and R is going this way. There will also be a shear stress, which I'm going to assume goes in this direction, and we will call that tau rz. And that's acting over some length that we haven't really defined, that we'll call L. This L is not the same as the mixing length L, it's just an L that we use for how far down the pipe you're going. If I do a simple force balance on this, I will have a force due to pressure on the left-hand side and a force due to pressure on the right-hand side, and essentially a force due to the shear stress applied over the surface of the cylinder. So as a result, what we find is that tau RZ, I would encourage you, by the way, to work out this result. It should only take you a couple of lines, is equal to R over 2 times delta P divided by L. And actually, I guess since I'm here in my office, we can actually go over that derivation since it doesn't take terribly long, and you can just skip this derivation if you know where that value came from. But let's do it real quick just to remind ourselves. If I look at the summation of the forces in the x direction, I know that has to be equal to 0, and I will have the two pressure terms, P1, or sorry, this is the summation of forces in the z direction. I changed my axes on this. So that'll be P sub 1 minus P sub 2 times the area that those are acting on, which will just be pi r squared. I haven't defined how big this entire chunk is, so really this r would be more appropriate going all the way up to the wall. The actual wall of the cylinder might be way out here. We haven't gone all the way out to the wall. This holds regardless. So we would have that term plus that shear stress tau RZ times the area that it's acting on, which is the surface of that cylinder, 2 pi RL. So that's all I mean by the force balance. I can rearrange those terms, and I find out that tau RZ is equal to R over 2 delta P over L. So if I want tau naught, did I have a color for that? No, not really. If I want tau naught, that is simply equal to tau RZ evaluated at R is equal to big R, which will be big R over 2 times delta P over L. And so you've got an example in your homework problem where we will ask you to evaluate tau RZ at big R over 2. That's not a problem. You are still free to come back here and plug that into this equation. This is a very general equation. It comes from nothing except a force balance, or really a momentum balance. So you're going to come back to that in, let me check here. This is going to come up in problem 4b. You will need that equation for 4b. But at any rate, now we have an expression for tau naught. We have a bunch of expressions here for laminar buffer and turbulent cores. So let's see an example of how you might use this. So this is also one thing that you're going to have to do in your homework. Let's say we wanted you to find the turbulent viscosity eta evaluated at R is equal to R for turbulent pipe flow. As soon as we say eta in reference to pipe flow, you should know that this is turbulent flow. That's the only time this eta shows up in this kind of a discussion. We're going to have a few more discussions that involve new definitions of eta. Just be careful you don't get them confused. In your homework, I believe we're going to replace this and simply say R is equal to R over 2. This, I believe, is in your homework problem 4. So the procedure is going to look the same, except I'm giving you an example at a different location. Your equations are going to look different. So where do we start? Our starting location is to say I need to know tau RZ, or tau YX, it doesn't really matter, you can pick one in this case, evaluated at R is equal to R. That will be equal to mu plus eta times dv bar, dvx bar, dy. One thing to note, your homework and book will usually drop this bar, because when we're talking about turbulent flow, that time average velocity is implied, right? It's just assumed that you know that those velocity profiles are always the time averaged ones For this example, I'm going to keep it around. Just beware when you look at your book's equations or even those notes on your homeworks, that bar might not be there. So our solution procedure is to evaluate first the left-hand side. So the left-hand side is going to need, tau is going to look like an r over 2 times a delta p over L. And then we're going to have to get this velocity profile from the law of the wall. Once we have those two expressions, we can isolate eta, which is what we're trying to solve for. So let's look at tau rz first. If I evaluate tau rz at r is equal to big R, remember this is exactly the same as tau naught. So that's really all the further I have to take it. In your homework problem, what you're going to find is that this will have to be actually equal to that r over 2 here. Oops, didn't mean to do that. You'll have to use this in your homework problem. That still holds here, but it just so happens that tau rz evaluated at the wall is tau naught, so I can save myself a little bit of math if I actually leave it as tau naught. And so that is going to be equal to the right-hand side of our equation, which is mu plus eta times d dy, and so I need an expression here. And this expression, remember, is going to be equal to v bar in the x direction. Or I guess really the z. I'm sort of mixing up my x's and z's here, but I assume you're following along okay. So I need an expression for Vx bar because I am in turbulent flow. I know I'm going to need one of the laws of the wall. If I evaluate one of these expressions down here on the bottom, I need to know, am I in the laminar sublayer, the buffer layer, or the turbulent core? In order to figure that out, I need to know what is my y plus value. Well, y plus, if I look at my definition of y plus, which is admittedly getting a little messy up there, y plus is equal to wherever I am with y times that quantity square root tau naught over rho divided by nu. Well, if I am at the wall, then big R is equal to R, and here I'm going to circle it. If I use this expression, and I substitute little r is equal to big R, I find out that y is equal to 0. So if y is equal to 0, y plus must also be equal to 0. If I put a 0 in here, I will get a 0 over here as well. That implies that this y plus is also 0. So I am in the laminar sublayer. If I'm in the laminar sublayer, then I know that v plus is equal to y plus. And so if I substitute that in, what I find is v plus is equal to, Vx bar will be equal to v plus times square root tau naught over rho. Sorry, I forgot how to move over here. Oops. So I'm just going to sketch a couple of intermediates down here. I have found that I am in the laminar sublayer, therefore v plus is equal to y plus. And if v plus is equal to y plus, then Vx bar will be equal to simply tau naught over mu times y. So I've just substituted in quite a few terms here, but all I've done is use the definitions of v plus and y plus that I have back here. And remember, we don't evaluate that at the wall yet. We actually only evaluate this term, the differential term, at the wall. So we have to get that expression first, then take its derivative, then evaluate it at the wall. So my expression for Vx bar will be simply tau naught over mu times y. So if I clean that up a little bit, get rid of some of my comments. So I need this quantity eventually evaluated at the wall. I'm going to get rid of my little scratch work down here. If I take that derivative, what I find is that first term is a constant. This is a constant. And so I'm just left with d dy operating on y, which is just 1. Kind of convenient. Yours will not be quite so convenient on the homework, but it won't be terrible. So what I have is tau naught is equal to mu plus eta. Remember, d dy is 1, and so now I have a tau naught over mu. If you rearrange this equation, what you will find is that in order for it to be true, eta has to be equal to 0. Now that's sort of an odd understanding of eta, right? It's a turbulent viscosity, but I just said it's a turbulent viscosity, so how, if the flow is turbulent, how can the turbulent viscosity be 0? But remember, we're in the regime that is called the laminar sublayer. That's why it's called the laminar sublayer, is because the turbulent viscosity is 0. In your homework, you will not have a 0 turbulent viscosity. In fact, it'll be really quite large. But in your homework, you're going to follow approximately this same solution procedure, except you're going to have a different law of the wall for V+, and your tau RZ, or tau YX, will be evaluated at a different location. So your math will look a little bit funnier, but your evaluation procedure will look the same. And so that brings us to the last thing that I want to bring up, which is a very important conceptual relationship. This is how we are able to go out and measure one thing and figure out all the other stuff. So this is an important concept that links a lot of the topics that we've just been talking about. One of the first things that we learned how to measure was a delta P. Right? We saw lots of different ways to measure delta P, static probes, stagnation probes, etc. Just last week we saw that, well, if I know delta P, I can move back and forth between my friction factor. And how did I do that? I needed the energy Bernoulli, and I had to combine that with a dimensional analysis. We went over that derivation last week. Here we see the other side of the equation, which is that if I know delta P, I can also get the shear stress at the wall, or really the shear stress anywhere. And we saw that this works because we just derived that relationship by conservation of momentum. What was that relationship? That was this relationship. So we saw that the shear stress is directly proportional to the pressure drop. So this very important concept allows us to measure any one of these variables. Most often the one that's easiest to measure is delta P. And from delta P, we can get expressions or numerical values for the friction factor or for the shear stress. And that's a very important link that brings together almost everything that we've learned in the class so far. And the important key is if I measure any one of these, I can immediately, by theory, figure out what the other two are. And so this is the last topic that we'll have for turbulent flow in a pipe, or really any kind of a flow in a pipe. What we'll see in the next lecture is what happens when we get outside of the pipe and start flowing over objects like flat plates or airplanes or whatever, dolphins. We might look at dolphins too. Thanks for watching, everyone.